Welcome to another lecture. The lecture today will be about two papers of John Conway, the late John Conway. He just passed away recently, and he was one of my mathematical heroes, let's say. I pretty much loved reading any paper of his. I pretty much watched every video there is online of him giving lectures or just talking with the people. I enjoy very much his books. I read at least two of these books already, and so this would be very small. I'm just paying my respects to him in this giving this lecture, let's say, and also it's about the Collatz Conjecture. Okay, so the paper, it's FRACTAN. The FRACTAN paper, there is only one. It's a simple universal programming language for arithmetic. So this was in 1986, and there was a previous paper which inspired this one. My fan was on, so it was making some noise, sorry. And the second one is unpredictable iterations. This is from 1972, and it is one of the earliest papers about the Collatz Conjecture after Collatz wrote his paper. Both papers are by John Conway. Okay. So, so this paper studies the Collatz problem in regards to its place in the world of problems that it comes from. Okay, so you can ask about what about these other similar problems. For instance, the 5x plus 1. You can ask about these sort of things, and you can also ask the broader question is, where is the Collatz problem placed in this space of problems which are related with the Collatz conjecture? And this is the point where he started in his unpredictable iterations. He proved that there is no algorithm to decide, given a Collatz type problem, if and an integer n, if you iterate that specific Collatz type map, if eventually it gets to 1. So there is no algorithm for that. So in the sense that the problem is undecidable. Okay. So that will be one of our first results. And then later on he wrote this paper basically giving a broad framework about what the stuff he did in the unpredictable iterations, and there is some very nice mathematics behind it, and some very say fun things to do. Okay, so first of all, let me start talking about FRACTAN. Okay. So what is FRACTAN? FRACTAN is a you could say a computer language for programming, but Conway always thinks of his stuff, I guess, in terms of games, and even you can think of no-player games if you like. So you think of FRACTAN as a game. So to play the FRACTAN game with fractions. So the FRACTAN game is a game it has fractions f1, f2, up to fk, and that will be my notation. So you just have a vector of fractions, and what you want to do is the following. You start with an integer n, and then you multiply and let me also close my windows. Yeah, so today is a hot day here in Bonn. Okay, so start with an integer n, and you just multiply the integer by the first fraction that makes it into an integer. So you multiply by the first fraction that preserves the property of being an integer. So you multiply by the first fi such that n fi is an integer. So let's say such that n prime, which is n fi, is an integer. So that's the game. So start with an integer and just iterate that process. Okay, and if you can't do that, if such fi does not exist, then what you do is just the game halts, stops, or halts. Okay, so that's it. And then you're left with an integer, and that integer will be the product of your computation. Okay, so so maybe in formal language you have a vector of fractions. Let me call it vector capital F, and you have a function, let's say phi f of n, which will be just defined as n fj if n fj is integral and n fi is not integral for 1 less or equal than I less than j. Okay, that's the... And what you do is just iterate this map, okay? Whenever you can, of course, because you can iterate and then you end up with something that you can't iterate, then you halt. Okay. Okay, so maybe let's just give some example. Maybe we can give the example of a game that adds up two numbers. So maybe suppose you're giving the following game. So what I do is I just 5 and then pass all those 5s to the 3s. So suppose you start with this game, okay, and suppose you start with an integer n equals 2 to the a, let's say 3 to the b. Okay, so what it does is, well, you have to multiply by the first, so it's just going to make all those 2's, so after a bunch of iterations, it's just going to make all those 2's become 5's. Great. And then, because, well, whenever I can divide by 2, then I have to multiply by the first fraction. And then it's a 5 and a 3, and I can't multiply by the first, but I can multiply by the second. Then after a bunch of iterations, we get a all this A moves to B. Okay, so this FRACTAN game adds integers. So it's the arithmetic function that is, you can identify it with the arithmetic function that adds to integers. Now already kind of revealing a bit of the magic behind all these things, okay? And you can come up with all sorts of things, okay? And so what's the relation with the Collatz conjecture? And again, when it gets to, maybe going back to this point, when it gets to 3, there is nothing to divide anymore. It can't apply, so the game halts. So whenever it starts with something like this, you get something like that. Okay, so it's properly adding, it's the addition function, if you like. Okay, so what's the relation with the Collatz map? So in general, you could think of a Collatz type function would be something like Gn is some an and n plus bn. So recall that our map was just n over 2 n even 3n plus 1 over 2 n odd, where an and bn are fractions that depend only on n mod some large number of v. Okay, so they are indeed periodic functions on n. So, so this is what is called, G is what's called a, maybe if you want to look for more examples of these functions and theory behind it, is a d-partite function. Okay. So why that would be a proper generalization? If you think about the Collatz map, first maybe an easy way to generalize is to set up some, take some big number v, and in each residue class mod d, so given an n, if n is in a particular residue class mod d, then you do something. That's exactly what we're doing here. And this something should be something linear on n. So that's why we write it in this way. Okay. Okay, so the Collatz map in this way is then realized if you take, so for instance, so C is realized by what? By taking an, bn to be equal to a half 0 if n is 0, 1, 2, and 3 halves and a half if n is odd. Okay. So that would realize the Collatz map. Okay. So the particular case, so if you think about, well, this Collatz type functions in this way is not guaranteed that you, whenever you start with an integer, it gives you an integer. But that's a very general class of Collatz type functions. Okay. Yes, but observe that these fractions here will all have denominators. So if n is a multiple of the largest of the minimum common multiple of all the denominators appearing in A and B and in B's, this will be a finite set of fractions, then g of n with a proper integer, for instance, if you can think of this way if you like. So, but in general it's not guaranteed. Okay, so the particular case, so the case where bn are all zeros, okay, is exactly corresponds to the case where you just have a function that maps integers to fractions, and then but gn over n is periodic. In the sense it's periodic. Okay. If the diperiodic function is a function of fractions, of course. So it maps n into fractions, and this will be a fraction, but it's a diperiodic. Okay. Okay. So in this sense, in this particular case, this here is a particular general class, subclass of the whole class of possible Collatz type functions, which would be this. So this class here will be a subclass of that. And what we're going to show is that for this subclass, there is no algorithm deciding whether this goes to 1 or not. Okay. In particular, there won't be an algorithm here, because if you have an algorithm in the full class, then therefore you definitely have an algorithm to deciding if I iterate g, if that goes to 1 or not. There will be an algorithm for this subclass, and since there isn't one for the whole class. Okay, that's the point. So okay, so now we can state the main results of this class. So and if you see here, basically this is almost like a FRACTAN game already, because this is diperiodic, which means that what I'm doing is basically taking the fractions here appearing in this, let's say in this, the fractions that appear here will be almost d different fractions, and for each residue class you multiply n by one of these fractions, and then that will be the result of gn. Okay, so it's almost like a FRACTAN game. The difference that the FRACTAN game is just asks for the thing to be integer as well. Okay, so the FRACTAN game will be almost like a proper realization of a Collatz type function that actually maps integers into integers. It's a problem that maybe won't be defined everywhere. Okay. So now we can state the main results. So following my list of theorems, that will be theorem 33. So now I'll introduce some nomenclature, some things that I will talk about later. So if F is a register machine computable function, well, I should say computable partial fraction. Partial just means that the function is not defined in the whole set of integers. So I will always be talking about functions that map integers into fractions or integers into integers, and partial here will always mean that it's maybe not defined in the whole set of integers. There is, if f is a computable partial function, then there is g with gn over n d-periodic, and g will be again a function that maps integers into fractions. and such that for every n greater or equal than 1, 2 to the fn is just g k of 2 to the n, where k is the smallest. In this case, g is not a partial fraction, so I should say there is g from the integers. Let me restrict to the natural numbers to rationals. So just to recall you, I use z plus as 1, 2, etc. Natural numbers start from 0 and q's the rationals. Okay. Where k is the smallest, k is the smallest such that yes, k is the smallest such that gk of 2n is a power, positive power of 2, let's say. Not positive, it's a power of 2. The way G will be built, it actually maps into natural numbers, but we can change. Yeah, I think it will be natural numbers anyway. So for every n greater or equal than 1, you have a maybe I should put here is that plus. Yeah, just positive integers. Yeah, so k will be the smallest power of 2. So basically what I'm saying here is that given a computable function, which I will define in a moment, you can realize it by a Collatz type function in the particular class where all the b's are zeros. So when all the b's are zeros, you can realize this function by, if you want to compute fn for this computable function, you just start with 2 to the n and just start iterating g, and the first power of 2 that shows up in this iteration, k is greater or equal to 1, of course, is exactly 2 to the fn, and this holds for every n. Okay, so I'm properly realizing the function f with this map, Collatz map G. Okay. So in my notes is actually corollary. The corollary is 35 in my notes actually. There is a theorem 34 in the middle. But maybe it's best to present the corollary now. And so there is no algorithm that given a function g with gn over n periodic decides and in here will be the classes of functions that actually map integers into integers. So G will be, let's say, Z plus 2Z plus, that decides whether or not there is whether or not for a given n gk of n equals 1 for some k. Okay, and there is an addition to this corollary that we'll present in the end, but only after other statements. So I'm going to erase this thing here. But basically what this is saying is that there is no, so consider the Collatz type functions where this is 0, and actually we have a function that maps integers into integers, but these so these a and had to be properly chosen in respect to the residue classes mod d of n, of course. But it's a subclass of all these possible generalizations of the Collatz function. And in this particular subclass, there is no algorithm. So in particular, there is no algorithm in the full class. So this is another way of saying that the problem is undecidable. Okay, you can't come up with beautiful proof that here is a condition that if tested shows that n goes to 1 at some eventually or not. You can't come up with something like this. It's undecidable. Okay, so that's the first. The second is we go back. Is corollary BB is theorem 34, and this theorem I will leave as a reading exercise for you. But after I prove a bunch of things, you will see that it's not that hard. So consider the following polygame. So we have 23 fractions. We call U. So here we go. There's 583 over 559, and then there's 629 over 551, and then 437 over 527, and then 82 over 517. 329, and then 371 over 129, 1 over 15, 53 over 86, 43 over 53, 3 over 47, and then 341 over 46, and then 41 over 43, 47 over 41, 29 over 37, 37 over 31, 299 over 29, 40. So there is actually a typo here in his paper. 161, 15, 527 over 19, 159 over 9, 1 over 17, 1 over 13, 1 over 3. So this is the list of fractions. Let's see if we have 23. 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. Yes. Great. So this is a universal game. Okay. So let fc of n be the function or partial function. Which is defined by this. So phi comes from the FRACTAN game played with this set of fractions u, but starting with c times 2 times raised to the 2 to the n. Okay, and then there is a k, and where k greater than 1 is the first, where phi u of k is the power of 2. Okay. Maybe the first of, sorry, not the first of the form. Maybe it's exactly the first of the form is a power of 2, but it's the first where k is the first, where is of the form 2 to the 2 to the m. So you iterate until you get the first number of this form, and whenever you get it, this m is defined as fc of n. Okay, and if you don't get it, then you don't define f. That's why it's partially defined. Okay. Then the conclusion is that then f0, f1, etc. lists all computable functions. Okay, it's a very nice result. Just with 23 fractions, you can list all computable functions. So listing computable functions in a very in a simple way, in some way, is actually something known. It's called Collini's normal form theorem, but this is just an explicit version of it. So it's known in computation theory that you can list all computable functions in some nice ways. But this is a very nice way and explicit of listing them all. And in the paper, Conway actually gives, I think, the first 1,024 functions, what they do. Okay, so you can go there for the list. Okay, and then he also gives the C, for which the function fc is the function that lists all the prime numbers. Okay. In addition to that corollary is the following. 35 prime, it is the following. If I define u tilde, just this set of the game with a set of fractions, okay, and then there exists a certain n naught such that phi k of u tilde of n naught, if I iterate this map, never prints, let's say, 1, but this is not provable. Okay, so that's in addition to corollary 35. Say 35 prime. Well, simply because this is a kind of a universal game that computes everything. So computable functions, I will explain in a moment what they are, but they're just like computer programs. So you can think of a computable function as just an algorithm in, let's say, C or C++ or FRACTRAN or Python, and take a paper language, or Java, I don't know, take your FRACTRAN, etc. So you take a family language. So basically, a computable function, you can think of just being an algorithm in some kind of language. And so this is basically computing, listing all possible algorithms. Basically, this computes everything. Okay? So it's not hard to guess that, well, if it computes everything, then you get in the world of the halting problem and these undecidable things. So that's why we get Collatz 35. Okay. And then we have one more theorem. So theorem 34 will actually be a reading. So this is a, let me write here, reading problem. Okay, but after I prove a bunch of things, you will see that it's not that hard. It's actually reading in like 3 or 4 pages, so you can get the idea. So the final is the prime game, and that's the most funny, most nice, awesome result of the paper. But it's not of John Conway. He's saying that this was, I think this was a result of Hickert, maybe Coxeter, I don't know, maybe Hickert, or Richard Guy, I don't know, one of these guys. So if let's say P is a prime game, so that would be a long list of fractions. over 33, 77 over 29, 95 over 23, 77 over 19, 1 over 17, 11 over 13, 13 over 11, and more, 15 over 2, 1 over 7, and 55 over 1. So the last is an integer. Okay, so I have these fractions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes, exactly. So when you play prime game, then let me arrange that part. So by the previous result, well, you can this is listing all computable functions. So in particular, it will be, so FRACTAN is computing everything. So you could guess that maybe I can write a function that computes the prime numbers. He also does the digits of pi, which is a bit harder than prime game. So I won't do here, I will stick with prime game. So if you have prime game and we start with n equals 2, then the next powers of 2 are 2 to the 2, 2 to the 3, 2 to the 5, 2 to the 7, 2 to the 11, 2 to the 13, 2 to the 17, etc. So the primes, so 2 to a prime in increasing order. Okay, so what I'm saying is that if you start with the 2 to the 2, with 2, and then you run prime game as a FRACTAN program and just start iterating, it will iterate forever, but then you just look whatever it prints, and then whenever you see a power of 2, you just take a picture of it. And if you do that, your pictures will be exactly these numbers, so it'll be to the prime number in increasing number, and you list all prime numbers. Okay, so it's a very weird thing, what the primes have to do with this list of 14 fractions, what they have to be special about it, and there isn't anything special about this 14 fractions. You could easily do it with, if you take all the primes in these fractions, for instance, and you just translate them, and so if you have a prime pi, then you substitute that by the prime pi plus 1. So if you do that in all these fractions, you get the same thing, but instead of a power of 2 here, you get a power of 3, for instance. So all the powers of 3 will list in the primes, and if you translate one more time, you have the powers of 5, and etc. So there is nothing special with these fractions, you will see. The only thing that is special here is how they change, what kind of things they do in the exponents of the primes appearing in these fractions. Okay, so what kind of operations they do. For instance, we already had a FRACTAN program that adds the exponents in the prime factorization of a number. So you could expect that other kinds of things could be done, and one thing that can be done is the algorithm to divide two integers. So you could put that, you can make that work with a bit more work, and then you use that to come up with these prime numbers. Okay. So we're going to prove basically theorem 33, and then corollary 35, and theorem 36. Okay, in that order. So, but before, I need to put some background. Okay. So far I've been talking about computable functions, or even mentioned register machine computable functions, and so I have to say what is a register machine and what is a computable function, and also I have to say what's a partial recursive function. So these are all background stuff, which probably you don't have. I have some of this because I did my 2 years before I changed to mathematics. I did computer science, so I know a bit about it. Okay, so let me put the background here. So maybe I should erase this already. Okay. Okay, so what's the background here? So first I have to talk about what is computation, and one of the simple register machines. So basically computation, we know nowadays, is just model in its core is basically just a model on this register machines, which one of them is a tape machine. Is a, you can think also as a kind of a register machine, is a Turing machine. So this is the well-known, is more well-known because of, I don't know, Turing became very famous. But so we've been working with Minsky machines, and these are very simple. Sometimes they even call just register machines because it's just the most simple model you can think of, a register machine. So so basically just have registers, R1, R2, R3, up to Rk, so a finite number of registers. Yes, and they can hold natural numbers, so they can store natural numbers. So n, which could be 0, 1, etc. For me, 0 is natural because if 0 is not natural to you, then you have serious problems. Okay, so what a register machine can do at any given time in its computation. So you can either add 1 to a register. You can subtract 1 to a positive register. So your instruction can be add 1 to register 1. And the next instruction is subtract 1 to register 1. And the next instruction is halt. So that would be a Minsky machine, for instance. You can either test if Rj is 0. Okay. Or Rj is positive. So basically, whenever you test if Rj is 0, so you have to give 2 possibilities. Either 0, you do something. If it's not, you do something else. And you can go to the next instruction. Okay. So for instance, a Minsky machine, let's say M, an example would be, and I will use this notation, you start, so that's the point where you start. So you start with all your registers with a certain initial configuration, so you can put numbers here, no negative numbers. And then, for instance, it gets to register A, let's say register 1, and it says subtract register 1. Well, whenever I subtract, I have to give an option. So if I can't subtract, so then I use a double arrow here, I halt. And if I indeed can't subtract, then you go to register 2 and you add. And then you go to register C, so R3, and you add. And then you go back to register 1. Okay. So I'll use some flow. So in this thing's flow chart, it's like a flow chart. So this has, so in priority order, is this, and then you get the next one is something like this, the next one is something like this, and then you just put more things. So first you do it with the one thing, then you do it with the second, etc. So this arrow here has more priority than this, so I have to do this. Unless I can't, then I do that. So go to this direction, unless I couldn't, because I couldn't realize this operation, R1 minus 1. So if I can't realize this operation, I can't, so that means register 1 is 0, then I halt. If I can, then I follow this. So this is saying that whenever you can do this operation, you follow with the first priority. So the first priority is actually realizing that, otherwise you skip. Okay, so this is all there is to a register machine. And what it turns out is that every computer we have nowadays is a register machine. They are the same thing. Okay, so computation is register machines at its core, and register machines are computations. Okay. So, for instance, what this register machine does. So if you start with, let's say, register 1, 2, 3 equal to A, B, and C, what it does is, well, you subtract A, and then you add in 2 and in 3, and then I go back and I subtract A again, and I keep doing this until I get A to 0, and then I halt. So that would be 0, B plus A, C plus A. So it's adding A to B and C. That's what it's doing. Okay? So that's a very simple Minsky machine. So in a nice way to encode this is with prime numbers. Okay, so you could put in, and my machine M, what it's doing is simply mapping everything to, I don't want to use the same symbols for the rest. So let's say C1, C2, and C3, and then it's just doing this C2 plus C1 and 5C3 plus C1. So it's just mapping this integer in this other integer and prime. Okay. So you can think of the prime numbers as being the registers of the natural numbers. Okay. So in this way, you define a partial function. So whenever you have a Minsky machine M, by this mapping using primes, you have a partial function. Why is partial? Because, well, if I start with an integer that, so let's say 7 has a register which will be a register 4, but the machine doesn't have register 4, so it's undefined. Okay, so that will be undefined. Okay, and also you could make a machine that just adds 1 to R2, and then adds 1 to R2, and adds 1 to R2, and so on. So here I'm not allowing loops. So loops not allowed. Okay, if you want to loop something, you don't put an hour like this. You just go from the same, and you put a copy of the same node here, and just go from one node to the other. So no loops. So this you can see as a loop, but not things like this are not allowed. Okay. Okay. So for any Minsky machine, you can come up with some partial function. Let's say f of m, and it's known, and I won't prove that for any and partial function fm, and you can actually show that these functions here is actually partial. So let me write so let me define this function here. So whenever you get a Minsky machine M, you can come up with a function fm. So using primes. So the fm will be what's called partial recursive function, which I will define in a moment. So what I'm saying is that for any Minsky machine, you define this function, and you can show that this function is a partial recursive function. And it's also known that for any partial recursive function, so we call it partial recursive function. And for any f, there is a Minsky machine that simulates it. There's a Minsky register machine, a Minsky machine, such that f is fm. Okay, so basically the functions that come up with associated with Minsky machines are exactly this set, which I will define in a moment, are partial recursive functions. Okay, and this is like a big result in the field of computation theory, is to show that whatever comes up. So whatever comes up with a Minsky machine is called a computable function. So a computable function is a function that has an algorithm that computes it. In what sense? In the sense of a Minsky machine. You have a Minsky machine or a register machine that actually has a code that computes that function. So that's called a computable function. And it's a big result in the computation theory to show that these functions that come exactly defined through Minsky machine is exactly this class of partial recursive functions, which are defined in another way, which and I will define in a moment. Okay. So basically, the result is saying that computable, which means register machine computer, equals a partial recursive function. Okay. So let me define what's a partial recursive function. So again, just to be clear, a computable function is defined as a function that can be computed via the Minsky machine, exactly with this association with primes. Great. And then it's a big result to show that this set is exactly the set of partial recursive functions, which are defined in a completely different way, which I will define now. Okay? So basically these are functions that have a certain domain in the integers and map, in the copies of the integers k. And again, whenever you have such a copy, so a partial recursive function in principle is defined in copies in the product of the copies of the integers, the natural numbers. But so I should say one variable here if you want, but it's not really, because also you can use the same trick with primes to map this function into integers by saying, you could use the same trick here, just as a comment. If you have a function like this, and you want the function actually defined on the natural numbers, you could use the same trick. You could just define this. So if you have a function like, so this is k, so this you take p1 to the a1, and pk to the ak, and you just map into, so now you have this, and you just do f of a1, ak. So now this f2 that will be a function for the natural numbers to the natural numbers, and this will be a proper partial recursive functions, okay? So in a way, I should say here one variable. Register machine computable one variable. So I should put one variable on both sides. This is one variable. Okay. And I will define here in the sense of multi variables, but again, with that association with primes, you can make any multivariate function like this to be a one variable function. So partial recursive functions is a function partially defined in the whole domain of copies, k copies of the natural numbers, such that, so this is a partial recursive function, something like this. So PRF is the smallest, is defined as the smallest class of partial functions like this. Such that that contain the constant functions, so of course I want to define something that's computable in a way, and can also be defined recursively. So constant should be there. Projection also. So let's say Pj of n1 mk is just mj. So it should contain all projections. So the function that just takes whatever is in the j coordinate and prints it, and also the successor. So it's not so k it's not fixed. Let me be clear about that. So it's the smallest class of partial functions which defined in some product of the Euclidean of the natural numbers. K is not defined. So in this class, we have functions defined in the natural numbers, and in N2, in N3, and so on. Okay, they include them all. Okay, in the successor function. Okay, and so it's the smallest class that contains these things and is closed by 3 operations. One is composition, but in a trivial way. So I have an f of x1 and xk. That will be some h of some g1 of x1 to xk, and dot 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 into some gl of x1 to xk. And h and g were already in the class. So you take any h and g already in the class, you do the composition like this, and you define f. Again, this identity here is just saying that define it like this whenever everything in here is well defined, and if it's not, then f is not defined in that vector. Let me erase that. There's 2 more operations. The next one is primitive recursion. So basically I define f of x1, xk 0 to be some initial g, so I have g and h to partially recursive functions. So I want to extend g to one more variable. So start with this, with the 0 here, and then what I do next. So this will be an h of y of f, the previous f, and all the previous vectors. So whenever you have 2 functions h and g like this, then you can define a new f like this, and that should be in the class. And the other property is minimization. Which is, I define f of x1, xk equals z if gi of x1, xk is well defined, positive for 1 greater equal for 0 less or equal than I less than z minus 1, and g of z x1 xk is 0. So basically minimization is saying that you start with, you take an initial g, you just use its first variable, you start from 0 and you start increasing, there's always positive until you reach 0. So all positive and well defined until you reach 0. So that will be minimizing in that direction, let's say, that's called minimization. And then you take exactly that point. Okay, so I won't get into what happens if you, how wide is the class. Just believe me, this is a huge class of functions. For instance, it includes the function that enumerates the prime numbers or the digits of pi, and etc. So it contains a lot of functions, so-called computable functions. So, okay. So it contains addition, product, taking powers, and etc. and all sorts of crazy things. So for instance, so what's the halting problem? Let me just make a comment here about the halting problem. So the halting problem is a problem in computer science that asks if you given an algorithm in the data, is there a universal machine that whenever you input an algorithm in the data, it outputs if that algorithm will compute that data and stop, or and halt, or it will eventually compute forever, or it's even undefined for the data, or it will compute forever, for instance. Is there a universal machine like this? And the answer is no. That was given by Alan Turing. And that's what is called undecidable. This problem of asking if a particular data in a particular algorithm, if that algorithm can compute that particular data, it's an undecidable problem because there is no algorithm that will give us that decision. Okay, so that's the halting problem, and very informal way of presenting. So one thing that is equivalent to the halting problem is the following. Is deciding if given n in the natural numbers and f a partial recursive function, if is fn defined. Okay. Okay. So you can think of, well, these functions by this result that I mentioned here, that basically these are exactly the functions that are computable by Minsky machines. So they can be seen as an algorithm, and n, the integer that you're given, is basically the data. So asking if it is well defined for that, it's almost the same as asking if you compute that data. So you can see why that should be equivalent to the halting problem. So I should say, so maybe, yeah. So basically, this is undecidable. So this is undecidable. Okay. And in the paper, Conway says, well, asking if a function is defined everywhere and it's identically zero is not undecidable, but it's exactly the same as asking if a given data, if the function is defined for that data or not. Okay. Okay, so now let's prove corollary 35. So in here I want to prove that there is no algorithm deciding if. So I want to prove that if I give G, N, and G, where G, so again, G is of this class of functions, where G is in this class of functions such that this is periodic. And G maps natural numbers into natural numbers. So given an entry in a G like this, I want to prove is, the question is there K with GK of n equals 1? So I want to prove that this is undecidable. Okay, there is no algorithm of deciding if I given G and I given N, if eventually we'll get to 1 or not. Okay, so suppose by contradiction there is. So suppose there is an algorithm A that decides if in G so satisfies this. Satisfies that there is a K with GK n equal 1. So suppose that there is an algorithm A that decides whatever it is. So if I input G and N on this algorithm, it spits out an answer. It does have or it does not. Okay. So I want to show that this is the same as asking that question. Well, because for any partial recursive function, or any partial recursive function is computable, okay? And we saw by the theorem before Collatz 35 that I can realize that function for any computable function. So for any f partial recursive function, which is the same as being computable, there is a G such that we have this realization where K is chosen to be the first K greater than or equal to 1 such that this is the power of 2, otherwise this is not well defined. So this is a realization. Whenever f is defined, that's the claim of the theorem of 33. Whenever f is defined for n, then you start with 2 to the n and iterate, and we'll get to a power of 2, and that first power of 2 will be exactly 2 to the f to the n, f applied at n. Okay, so then, okay, so so then what is going on here is that well, whenever f is well defined, if k, there exists a k that goes to such that this is 1, this is exactly as asking if fn is 0. Okay, so for instance, I could just define this f tilde function n, which will be 0 if fn is defined, and not defined otherwise. So for this function, there will be a corresponding g tilde, okay? Because this guy is partial recursive as well, okay? So basically, because basically this is like the indicator set of the set where a partial recursive function is well defined, and you can show that this is a partial recursive function as well. Okay, so there will be a proper G such that satisfies, which has this identification. Okay, so if I apply the algorithm for the data n and for the data g tilde, this algorithm A, so using A, it will tell if f tilde of n is 0 or not, and moreover if it's well defined. So it will tell exactly if n, if Fn is well defined. Because if Fn is well defined, it's exactly when F tilde n is well defined and is 0. This is exactly when I can iterate J tilde and get to 1, which is exactly what the algorithm A supposedly do. So, so we'll tell exactly if Fn is well defined. In particular, it's solving this problem. It's finding an algorithm that for a given f and a given integer n, if Fn is well defined, and that's indecidable. So this is a contradiction. Because this is undecidable. Okay. So there you go. So once you can realize any partial function, basically you won't be able, partial recursive function, you won't be able to tell if something goes to 1, because that would be exactly the same as solving the Holly problem. If for some given data, the algorithm will compute it somehow. So that is not surprising once you know these things. Okay. So now let me prove theorem 33, and then we move to prime game and finish. The theorem 33 is also not hard. So theorem 33 is saying that, okay, FRACTAN, with FRACTAN I can with this game I can compute anything. And one thing you observe is that any FRACTAN game is a function of this type. Any FRACTAN game is a function such that Gn over n is periodic. And the period will be exactly, we'll just take all the primes, putting the denominator of the fraction. So basically what I'm saying is that before I start the proof, so any FRACTAN game, maybe I said that the FRACTAN game is not defined when you cannot apply any of the fractions. This was wrong. You can always apply it. It's always well defined, because if you can't apply any fraction in a FRACTAN game, if you can't multiply, then the answer is just the thing you have. Okay, so any FRACTAN game is a Gn over n periodic. Word. So G will be then the phi from the FRACTAN game F. Okay. Simply because if you have your list of fractions, maybe it's FD, no, FK, sorry. Okay. This is periodic because if D is the greatest common of the least common multiple of all the denominators. Yeah, if you take the least common multiple of all the denominators, then phi f of d n divided by, sorry, it has to be periodic. So if I just do this, sorry, what's going to happen with the FRACTAN game? Well, I know that all the fractions divide this thing here already. So I will just get, so if I divide, so all the fractions will divide this guy here. So I only have to multiply this guy here. So whatever this guy tells the fraction game to do, that's exactly what the fraction game would do with the sum, because all the fractions times this t is an integer, okay? So this is periodic. So this equals exactly, so the fraction it will choose will be exactly the fraction related to n. So it will be exactly this guy. Okay. So the FRACTAN game is an instantiation of that small subclass of Collatz type functions that we were talking about. Maybe I said otherwise when I explained, so I was confused maybe. Okay. So all I have to do now is to come up with this function g. All I have to do now is just given a partial recursive function, I need to come up with a FRACTAN game that simulates it in the way I described, like this. Okay. But a partial recursive function is exactly a function that comes out of a Minsky machine, as I mentioned before. So I just need to show that for any Minsky machine, I can simulate this Minsky machine with a FRACTAN game. So it's not hard to yes. Did I put this as a problem? Yes. So only have to, from a Minsky machine, I have to be able to come up with a FRACTAN game that simulates it. But that will leave as a problem. This is not hard to show that given a FRACTAN game, produce a Minsky machine that simulates it. And this is not really hard, because just think in terms of prime powers, what this is doing with the register of the natural numbers. So you're multiplying by certain primes and dividing by certain primes whenever you apply F1, and that would mean adding up something or subtracting something from the registers, which would be the contents of the exponents of the prime factorization of your entry. So basically, going from a FRACTAN game to a Minsky machine is almost straightforward. The opposite is kind of a straightforward, but it needs some tricks, and John Conway is very good in doing those things. So he realized that this could be done. Okay, so yes, so okay, for instance, one thing you can do here is try, so for instance, as a hint, try to produce a machine simulating the FRACTAN game 2/3, 5/7, which is the one I put as an example of a simple FRACTAN game. So try to produce a machine that simulates this, and you will see that it's not hard to generalize the idea. Okay, so now let me go from a machine to a FRACTAN game. Okay. So basically the machine will be something like you have a start, and you have some instructions here, and then you have like this, or maybe something like this, to halt. Okay, that would be a Minsky machine. So suppose you have this Minsky machine M, and what I want to do is I want to come up with a FRACTAN game that simulates it. Okay. In the way that if I start with some resistors here, then with certain numbers in the resistors, and when I halt, I have a certain other configuration. So if you use the map with putting those resistors as the content of those resistors as exponent in the prime factorization of a natural number, that would be the input you have to put in the FRACTAN game, and the output, so when it halts, the output should be exactly the same output that it puts here, that you have here, okay? So the idea is that if I start with R1, RK resistors as C1, CK, and I get to something like C1 prime, CK prime in here, then in here I should get something like, if I start with 2 to the C1 over to the K prime CK, I should get after the same thing. Okay, so that would be the proper mapping. Okay, so how do you do it? So first of all, you enumerate. So there will be an enumeration here. So so you number all arrows in M. So maybe you have an arrow like this and an arrow like this. So what you do is you put a node and you put the number there. Or you put the node here and you put the number there. Okay, and this had to be number all arrows in M with distinct positive integers. Okay, and you will number the start and the halt positions with 0. And start and halt number with 0. Okay, so let me make an example there so it becomes easier to understand. So in a way, I'm spoiling all the joy of proving prime game from the gecko. By doing these things, see, prime game doesn't look like they're impossible anymore. Okay, so suppose I have a machine like this. Suppose I had this machine, R1 minus, and this would be R2 plus, and this R3 plus, and then this is halt. So by doing these numbers, what I did was to put a 0 here. So what I did is I put a 0 here, 0 here, and I just number all the arrows with whatever I want. So it's 1, 2, and 3. Okay. So so there will be nodes here, node here. So number all the arrows in M with distinct positive integers. That's not completely correct. Arrows in M not coming on or going to start or halt. With positive integers, okay? So for starting halt, just put 0, and for the others, you get things like this. Distinct integers. So let's put just 1, 2, 3. Okay. So suppose I had something like, I had an M, and that M went to some resistor Rj plus, and then it went to some other node N. Okay, so what's the fraction I'm going to associate with that? I'm going to associate fraction M. See, I'm always coming from some node to something else. Fraction M, and that fraction M will be what? So first of all, I'm assuming that this thing has k resistors. So let me use the primes P1 to Pk to store the resistors. And also let me put two extra primes. Let me use A and B for that. A and B. So these are primes. So this is the first prime, the K prime. So A will be the Pk plus 1, and B will be the Pk plus 2. Okay, I will use 2 extra primes. So I have to add j. So definitely I should put pj in this fraction. But then I want to guarantee that I have something in the end, and we'll see why. So we'll put b to the n, and then we'll divide by a to the n. Okay. If I have something like an m going to a minus, and this minus would then have 2 options. Let's say n and l. Then you have a pair of fractions, which would be, I have to subtract j, 1 to register j, so I need to put pj minus 1. And then I put then I put b to the n, exactly a to the m. But then maybe I don't do anything, so I don't put b, and I just put p to the l, a to the m. You have these pair of fractions. Okay. So then the FRACTAN game will be the fraction a over b, and then here you put f m. So suppose I'm numbering all of these things with distant integers. It doesn't matter, it just needs to be distant integers. But suppose I use m not distant integers. I could just then replace them by the numbers from 1 to m naught. So let me assume that just by reason of notation. So basically what I would say is that now you put all the fractions here with decreasing order of indexes. So it won't matter if you put any indexes from just distant and random number and random natural numbers greater equal than 1. But for notation purposes, it's better to just use the numbers from 1 to assert the number m naught. So recall, we also have the fraction 0 because this could be the node 0 going to something, and this also could be the halt, which would be 0 here. Okay, so we also have the fraction 0. So we don't have a fraction related with the halt, we just have a fraction 0. Okay. And to make it right, sometimes there is a 1 at the end. And so, and actually, so if there is a 1, then f would simulate, it will stop exactly at the point we need it, but then it would just keep repeating that number. It will never stop. It would just print the number to infinity. And so to remove that problem, so remove the possible 1 in the end. In the paper, Conway doesn't do that, but I guess he didn't care if the FRACTAN game would just loop forever, printing the same number. So if you do this thing for our example here, okay, so this was the example, so recall that this was the example that sent to A, 3B, 5C, to 3B plus A and 5. Maybe I didn't give this example before. I don't know. So this is the machine that if you use these guys as register, maybe register 1, register 2, register 3. So maybe I should put C1, C2, C3. Now that I think of, I think I gave this example. So that's what this machine does with these registers. So if you use that mapping here, the FRACTAN game, corresponding FRACTAN game would be 7 over 11, 11 over 6, 8, 6, 1 over 3, 4, 3, 6, 6, 5, 5, 4, 49, 3, 63 over 7, 11 over 2, and there would be a 1 here in the end, because fraction 0 will send 0 to 0, because we have this thing, 0 to 0. So whenever you have 0 to 0, it won't do anything here. This is raised to the 0, raised to the 0, you will get a 1 right here. So there was a 1 here, so we had to remove it. Okay, so if you use this, then this simulates, this FRACTAN game simulates exactly this operation. Okay, with this mapping. Okay. So let me show why this works, and then we move to prime game. So what's the idea? The idea is to run the machine M in parallel with the FRACTAN game, which it's a no-player game, if you like, with the FRACTAN game F. Okay, and see what happens, and see that whenever this makes one, whenever this computes something, runs one instruction, the FRACTAN game will run 3 instructions, and they will get the same result. Okay, so suppose I start with an N, which is P1 to C1, PK to CK, A to 0 and B to 0. Okay? And let me just erase B to 0 for the moment. It's B to 0 anyway, but I want to leave A to 0. Okay? So you had the starting point. You had 0, you went to some Ri, which could be plus or minus. Let's say it's plus for the moment. And you went to some number M. Okay? So what this did was the following. So this made N go to N prime, which will be P1 C1 plus 1. So let's say I put prime here. this is R. So this will be P1, C1 dot 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 PI CI plus 1 dot dot PK CK, and then A to minus 0. Okay, so this is the end. Okay, so this is the end for the FRACTAN game, and let me use the registers maybe. Yeah. So what happened here? I just added register I plus 1. Okay. So that's what I did in the machine. What happens in the FRACTAN game? Well, first, so recall here the fractions. I can't multiply by the first because there is no b in here. So I have to go to, there's no b in here, sorry. So I have to go to the next fraction, which is m naught. But all these fractions, f's, with some positive integer, they have something dividing by a. Okay, so I can't use all of them, any of them. I have to use f naught. Okay, and f naught is exactly the fraction related with this operation. Okay, so what f naught will do is will exactly add this and then multiply by well, f naught will multiply by b to the n divided by a to the m. So maybe I should put an n here. So this will multiply by b to the n divided by a to the 0. So nothing happens. Okay? And then the second step would be, yes. And then the second step would be, well, when you iterate one more time, then you, so I said 3 instructions that the FRACTAN game does. Exactly, sorry, it's just 2. Because I multiply by f naught, then I have to multiply again by this first fraction because that guy has a b and this guy can cancel that b. So replace all these b's by the a. So we got p1 c1 pi ci plus 1 pk ck and then a to n. Okay. So I started with p1 c1 to the k and a with nothing, which is exactly this number, and end up with the operation that I should do, which is just ci plus 1, and then with a to the n, which is the final point here. Okay, and in this part, we know that, so at point n in the computation, of the machine M, we had the registers. Let me say the register is a vector equal to C1 Ci plus 1 Ck, and that's exactly the powers, the exponents in, let's say, n prime prime if removing forgetting a c. A and the A's and B's. Okay, so if you forget these A's and B's, which is just using as an auxiliary memory, if you like, the exponents are exactly the same. Okay, so the first operation we did it right. Okay, so let me assume by induction. So assume by induction at time t. At time t in the computations of m. So at some point in the computation of this machine, we arrived at a point m that goes to some rj, could be plus or minus, and that could be something like this to a point n, or it could be something like this to the same point n. Okay, I don't know. Okay, so I didn't do here, I forgot to do the minus one example. But if you do the minus example, you get the same thing. I mean, if you put the minus here, either you have it or you don't have it, so you have those two cases. In all those two cases, you will get the correct exponents in this part of the n, and a to the power n, which is the node that you went to. Okay. Okay. So assume by induction that time t in the computation of m, so time t will be here. We have the registers with certain configurations, C1, CK, and in the FRACTAN game, we had n exactly with the same configuration, the primes exactly with the same configuration, and a to power m. Okay, so what I'm doing is I'm running m and the FRACTAN game in parallel. Whenever m computes passes through one node that adds or subtracts, the FRACTAN game does two steps. That's the induction assumption. The FRACTAN game does two steps, and in these two steps, it's not exactly two steps because you're first doing this and then you're applying the first fraction here several times until you make this b to be transformed into a. So actually I'm applying n times here the FRACTAN game. So exactly two steps. But you can see this is a two-step thing. So yes, so in this way you had, if you compute them in parallel and you follow them in parallel in this way that I'm explaining, you arrive at this point with the registers like this, and also with the n. So in the appropriate point in the FRACTAN game computation, you have this n with exactly this, and exactly this m, okay? Which is the time t thing here, okay? So what then happens? So again, I forgot to explain the minus one here, but you can do yourself, and you have two zero cases. So this is the base case of the induction, and I forgot the other two. There is also the possibility that this is a minus. So this could be a minus. So you then do that as a problem to see that the induction, the base case for the induction holds true. Okay. So now what happens? Well, again, the same thing happens. Well, in here, just have to add or subtract register J. So let's say I add, because subtracting is also easy to do, but boring. Suppose I add, for instance. So I have my fraction, which I have my number n. I have to multiply by one of these fractions. Okay, but I have an a to the m here. Okay, and these fractions are listed in decreasing order. So I can't multiply by this if this m naught is greater than this. I have to multiply by the first fraction, which has a to the m in the denominator, with an m which is smaller than this m here. Less or equal, okay? And that would be, if you follow these fractions, it would be exactly the fraction fm. Exactly the fraction numbered by the exponent of a here. Okay, so in the FRACTAN game, I would actually multiply this by the fraction fm, and I will get exactly, this was rj, so pj, cj plus 1. I'm assuming that this is a plus, okay? And then pk, ck. And then what I would do is exactly put the final thing here, which is to the n, and then remove all the a's. So I would just put the b to the n here. And then I have to multiply, then I apply again n times. This would be n times. So this is again that two-step thing. I will apply this first fraction and transform all these b's into a's. So I get to the other side, which will be time t plus 1, let's say, with exactly a to the end node, end point here, and then I can move on. Okay, so you can see this is roughly explaining the induction argument you can do, but basically this finishes it. Okay, before I start the prime game, let me just review what we did here in a moment, just to be clear. Okay, so we have Minsky machines, and those have resistors, R1 and RK, and they output something. Once you put that as input, they output something, which is something like the R1 prime, RK prime. But then if you use the coding, if you use primes here, you can then use this to come up with a function which will be exactly this one. Okay? And what I mentioned was that this is what we define as computable functions. These functions f, coming from Minsky machines. And this is exactly coincides with the set of partial recursive functions in the way I described recursive functions in the way I described before. Great. So that's the k variable function. You can make it to a one variable if you like. Again, by using the encoding in here. So what I proved here is that any FRACTAN game can simulate a function like this, which in the FRACTAN game, I made a FRACTAN game f, which I give an input which is p1, r1, pk, rk, and the FRACTAN game outputs p1, r1, prime, pk, rk prime, and then something which will be, if I don't put that 1 over a in the end, which would be a to some number, let's say m. Okay, so it's simulating exactly the FRACTAN. Exactly the Minsky machines. In particular, I'm simulating every partial recursive functions in k variables. But if I want to put exactly in the form of the result, then what I can do here is I can do a projection and just map in this into the prime p1, which is 2 by the way, 2 to r1 prime. Okay. And so in this way I create a new function. So let's say the function f r1. This way I create a new function, let's say f tilde, which f of r1 is exactly input is exactly, you put the Minsky machine is exactly input with r1, and then the rest is just filled with 0m, and that will output some number like this, and then you get a projection, and you get just 2 r1 prime. Okay. Okay, so that would be a computable what you do is you just you just map it. We better if I just do the projection, put it to r1 prime. Okay, just project the first variable. So just let me not Okay. And it turns out that since these are all computable functions, if we project this whole class in this way, this would all be all computable one variable functions. Okay, which is all partial recursive one variable functions. Okay. So, and this whole thing here, which is this thing here is another Minsky machine. Let's say M tilde, because you can do projection inside a Minsky machine. Okay, so therefore, if I had this Minsky machine to start with, okay, so if suppose I start with a one variable computable function. Okay, then I start with an M tilde like that. So if I do the FRACTAN game exactly as I said before, you will simulate, and you start with P1 to the power R1, okay, which is 2 by the way, this is 2 to the power R1. You will get in the end 2 to the power R1 prime, but R1 prime is exactly this F tilde of R1, okay, and that guy times some A to the end. And there won't be any other power of 2 in the middle of computation, because if you look in every single computation, we always have these B's or A's multiplying something. So there isn't a power of 2 in the middle of computation. So then if you add the extra 1 over A, okay, so then if in here you use a FRACTAN F with the 1 over A in the end as well, then the very first power of 2 that will show up will be this guy, okay? So that was kind of implicit in the demonstration, but I thought to myself that you could figure out, but it's better to be explained vigorously. So whenever you have a one variable computable function, you can compute with the Minsky machine exactly in the way I explained. That will be a machine that if you with K register, that if you enter this R1 and a bunch of zeros, it will print out, in the end should be a projection, it will print out just an integer. So it would print out, basically what it would do, it would print out just R1 0 0 0 0, okay? Because there will be a projection in the end. And then you just take the first coordinate, that would be a computable function. Moreover, that would be the set of all one variable computable functions. So if you use this mapping here to a FRACTAN game, you will start with something like this, and you get exactly what you want in the end times the power of A. But then if you add that 1 over A in the end, then you get this. Okay. So in his paper, Conway just mentions that this will work and that they will simulate and etc. It doesn't really get to in the details, and I think these are the things that he didn't mention. Okay. So now let's move to prime game, which is the most exciting part. Let me raise the whole board. We need the whole board. So Conway once said, I think it was in a number file interview, that whenever you have something like one of these weird computational devices, like the game of life, for instance, and then if you can't predict what it does, then probably it's because it can do anything. So it's exactly as I said, if you can't compute, if you can't predict what this Collatz thing is doing, so basically it's because it's computing on it's a computer, it can compute basically anything. It's just that you can't really understand what it is computing, but it is basically computing everything. So, so basically if you can add, and if you can copy registers from one to another, add a register, subtract a register, and then go to the next instruction, if you can simulate that in your computational device you came up with, then this will mean that that computational device is universal. It can do whatever computation it can, in the sense that it can compute every computable function, or in the sense that any partial recursive function can be written in the code of your computational device. That's more or less the heuristics. Again, in my point of view, I'm not an expert in this field, as you can clearly see. Okay, so priming. So let me put the list of fractions in some visible place. Let me see if I put the list of fractions here. So we'll factor all the fractions to make it simpler. So the first fraction was this, and then the second was this one, and then we have 19 over 3 times 17, and then 23 over 2 times 19, and then 29 over 3 times 11, and 7 times 11, 29, and then 5 times 19, 13, oh, 23, sorry, and then 7 times 11, 19, 1 over 17, 11 over 13, 13 over 11, 3 times 5 over 2, 1 over 7, and 5 times 11. Okay, so let me give names for this. It will be A, B, C, D, E, F, G, H, I, J, K, L, M, N. Okay, these are the fractions in priming. Okay. So before we start, let me just give you what's going to be the idea. So this was designed in a way such that we have the following. So basically this was designed in a way that if you start with n, oh, I shouldn't put n, there's an n here. Let me put then let me put what's the next one? N, P, Q, I'd say R. There are no, there is an R. So if I start with this, and I have one less equal to D plus N. Then after I compute everything, so we start computation. This will compute forever, by the way. But at some point, I will get to a number which will be, after several computations, which will be 5 to the n, 7 to the d minus 1 times 13. And this would always be the case if d does not divide, which I'll be using this symbol here, does not divide d, n. And it will, if I start with the same thing, and d does divide n, then after several computations I will get to 5 to the n, 7 to the n, 5 to the n plus 1, 7 to the n, 13, and that is if d divides, and that I will be using this symbol n. Okay, so that is the claim. So I'm claiming that you do that, and then after several iterations, the first number of this form again will be this guy if it does not divide n. And if it does, the first number of this form again will be that guy here. And moreover, and in this final guy here, and in here, so in here, in this computation here, no power of 2. No power of 2 showing up. And in this one, there is exactly 1. there is exactly 1 power of 2, which will be 2 to the n, but only if d was 1. Okay, so this is part of the claim. Okay. So the claim, so that will be the procedure. So this machine was designed in this way. Whenever I start with something like this, it will actually test if n is divisible by d. If it's not divisible by d, then there is no power of 2 in the middle computation. If it is, then there will be, but only if you are trying to divide by 1. Okay? So if you want to go ahead and think why this will imply the result, you can go. It's a very simple deduction from this claim. I would do it anyway, that it implies the result. Okay, but to prove this claim, we first need to kind of take a look into some loops. Okay, so the first loop is this one, which if I start with a 2 to the a, 5 to the n, 7 to the d, 13, and then I have to apply this, and then we get to, I will just add the d, which was in the 7, to the 2's, and I will copy also what was in the d to the 3's, and I will subtract the d of the n, and I replace the 13 by an 11. Okay? So let's see. So there are a bunch of these loops. Let me explain, let's say, at least the first 2, and then the rest I will just write that they work. So this one, why it works. So suppose I start with this. Well, there is a, oh, and I have to say what this is. This is n greater or equal than d. I'm assuming that n is greater or equal than d in this loop. So this is the first loop, and we have a list of 1, 2, 3, 4, 5 ones. This is the first one. So why this works? Well, we are here. So again, when I'm multiplying from the left, okay, from the right. So this is what I mean is I'm multiplying n by from the right, yes, n, a, p, d, j. Okay, not to be confused by multiplying from the left. So what I'm doing here, so that's what I mean. I'll always be multiplying from the right. So, okay, so I do have a 7, and I do have a 13. Suppose that these greater or equal than 1. So I will divide by this, okay? And then I will remove that 13, and I put a 17, and remove one of the 7s, okay? If d is greater or equal than 1, then n is greater or equal than 1. Therefore, I do have a 5, and I just put a 17, so I can divide by b. So I remove that 5, and I put a 2, so that's why I'm increasing here, and then I put a 3 as well, so that's why I'm copying the contents of 7 to 3, because I removed the 7, I remove the 7, then next I put a 3, okay? And also removing a 5, at the same time as I remove a 7, so I have to remove a 5 and put a 3, remove a 5 and put a 3, and also put a 2. And I put back the 13, okay? So now, n is greater or equal than d. So if d minus 1, so the first step here would do just this. Oh, there was a 3. 3, 5 to the n minus 1, 7 to the d minus 1, 13. So that would be just applying by AB. Okay. So I can keep going as long as I have a 7s. Okay. And if I don't have a 7, it means that I got into 2 to the a plus d, 3 to the d, and 5 to the n minus d, no 7s, and a 13. So what's the next number I can divide? No, I cannot. I have to divide by j. That's the first one, and then we replace that 13 by an 11, and we'll get to this position. Okay, so that's the first loop. Second loop. What if we don't have that? So what if we have a 2 to the a? So that will be again a, b, x, and a. So what if I have a 2 to the a, 5 to the r, 7 to the d, 13, and I know that so r was the n, so let me maybe put an n here. So it's the same as before, but now I will assume that n is less than d. Okay. Of course, greater or equal to 0. Okay. So what happens now? Well, let's see. Well, I can multiply by a and then by b again, as long as I have sevens, which was the same thing as before. So I can do a, b, as long as I have sevens and fives, because I'm dividing by 5 here. So I have to apply this n times. Okay, so I remove all these guys, n here, this will vanish, and I will add these guys to here, and d n in a 13. And then what's the next one I have to apply? Well, I can definitely apply an a, because d is strictly larger than n, and then so that will cancel 1 7 and the 13, so that will be a minus 1, and then I'll have a 17 here. Let's see if that's right. Oh, and I forgot about the 3. There is a 3 here. A plus n and 3 to the n. Yeah, great. That's another loop. Let me see 3 other loops. And then these ones I will just write, they work. So this will be EF K. So that will be 2 to the A, 3 to the L, 5 to the N, 7 to the B, and 11. And if I do an EF L K, then I have a 2 to the A, so the 2 is left unchanged, the 3 is removed, 5 is the same, then whatever it was in 3 is copied to B, and add up to the exponent and exchange 11 by 13. Let me put another loop here, DG H. What is that loop? So suppose I start with a 2 to the A, 3 to the L, 7 to the D, and 19. So apply DG 8 times and then an H. That will make the same. And then please check. And then I have this loop. This loop is a 2 to the A, 7 to the D. And then I have this, and this would be a 3 to the A, 5 to the A plus 1 and 11. And the D's are completely cancelled here. Yes. And that's it. These are all the loops I want. So now let's start with the prime game. So what I want to do now is to prove the claim. So now let me show what the claim implies So these are the loops. So let me show why the claim implies the result. Okay. So suppose I start with a 5, 2, 7, 13. Okay, suppose that I start with this. Well, 1 indeed divides 2. Okay, so by the claim, I should get to a 3, 7 squared 13, and the only power of 2, d is 1, will be exactly 2 to the n, so 2 squared. So maybe I should start with another. I should start with just 5 times 13. So yeah, maybe as an exercise, if I start with a 2, because in there I was the first power of the 2 squared. Oh, but the 2 is to a prime, yes, sorry. Got confused for a moment. Yeah, so you get a 2 squared, which is the first prime, and that will be the only power of 2 in this computation. Okay? And then I get to this point. Now, 2 does not divide 3. So, by the claim, it will get to 5, 3, 7, 13. No power of 2 in here. But now 1 divides 3, and d here is indeed 1, so it will get to 4, 7, 3, 13, and the only power of 2 here would be 2 cubed. Okay, when you keep going, then you see whenever you have a composite number here in the exponent of 5, you will, before you get to 1, you get to a point where d divides this number, and then we just jump to the next one. So for instance here, I will compute, and then we'll get to this, no power of 2, and then I will get to, so this divides, but there is no power of 2, so it's 5, 7, 4, and 13. And this keeps going, so the next power of 2 will show up, this doesn't divide, so this 4 will decrease until it gets to 1, and then at some point you get to 6, 7, 5, 13, and there will be a unique power of 2 here. Going to be 5, and all the other computations there wasn't any power of 2. So exactly when you get to 5 to a prime number, that you get in the game when you reduce d several times, d minus 1 minus 2 and 2 to get to 1, and then you get to the second part of the claim, and in the middle of this computation you will get a 2 to that prime number. So that means if you start with this guy, this is a deterministic game, the path, exactly the point where this guy showed up, the path will exactly get 2 to the 3, 2 to the 5, and 2 to all the prime numbers. And that will finish the proof. Okay. So that shows that if this claim is true, then we finish. We just have to show that this claim is true. So maybe I should do this computation. I have like 1, 2, 3, 4 lines. So maybe I should do where we can do this here. Just erase this part. This is n less or equal than d, and this is n. Oh, sorry. This is d less or equal than n, and this is n d. Then you put all these loops here. So let me go from this part to this. Maybe we can do it. Okay. So now we have to prove the claim. So suppose I start with 5 to n, 7 to d, 13. Then, well, this is exactly as in the first loop here. So I just apply a, b to the d and the j, and I get to 2 to the d, 3 to the d, 5 to n minus d, 11. Okay, that's the first loop. Then now I'm in the position of applying this third loop here, the EFK loop, because I'm exactly having these numbers. So 7 here is with the b equals 0, etc. So what it does, it just copies the contents of the 3 to the 7s and moves the 11 to a 13. So 2 to the d, 5 to the n minus d, 7 to the d, and 13. So that would be EF d times k. Okay, right. But now I go back to a possible application of this guy. Because the 2, 5, 7, and 13. 2, 5, 7, and 13. Okay, so I can keep doing this. Let me do it one more time. So that I have an A, B, and how many times I apply D times D and then a J. And then what I will do is just add this to this, and then I will put a 3 to the D and a 5 to A minus 2D, and then a 11. Okay? And then I go ahead and apply an EF again. So if I indefinitely apply these guys, okay, I will just be adding up this thing, cranking up this number 2 to a 3 and a 3 here. Oh, sorry, I still have to apply one of these. So let me apply one of these before. So just copy all the contents here to a 7. Yes. So let me see what's going on in the end. Yes. And this changes to 13. Okay, so this was this, and then this again. Yeah, great. So if I keep going in this thing, I'll just crank up this 2 until I can't do anymore. I don't have 5s. No more 5s. That means, so first let me write, maybe I should do this before. So if I write n equals some qd plus r, where 0 is less equal than r less than d. Okay. So crank up this thing until I get here q times d minus n. So we'll get an r. Okay, this is still d. And this is q times d. Yeah, exactly. Okay, so just apply, so you had this process and you came up to the same guy, just apply this process over and over until you get to this point. Great. So now maybe I should go up. So what I do now is, I just apply, so here and now I am now in a position of applying the second guy, because this is exactly when the powers of 7, you have more powers of 7 than powers of 5. And here is exactly what you have, more powers of 7 than powers of 5. Because d is greater than r. So what it does is simply, it adds up whatever is in 5 to 2's, and reduce that to the 7's, and one more, and then replace this by a 17. So we will add up the r to this guy. So that will be exactly a q to the n, and then it will reduce d minus n minus 1. Oh, and we also have a 3 to the n, which is copying the contents of 5, so 3 to the 5, so 2 to the n, 3 to the r, and then this is a 17. So this will be a A, B, how many times? Exactly the number of times of 5, so R and then A. Yeah. Great. So now we have two possibilities. You can even, maybe we can do it here. So you can even go up or go to the right. And I go up if R is positive, and then go to the right if R is 0. Okay? So if R is 0, let's say if R is 0, so if R is 0, well, if R is 0, we just have 2 to the n, 7 to d minus, oh, this was R, sorry. R minus 1 and 17. So what is that? That is a 2, is a 7, and a 17. So I have 2s and 7 and 17. So what I can apply here? I can apply this, can apply a C, no, I cannot. 2 7s and 17s. I do have a 17, but I don't have a 3 because R is 0. So I cannot. The next, the very first one will be this guy. It's a 17. So I have to apply an I. So R equals 0. So apply an I. So the I would just remove the 17, and then I will get 2 to the n, 7 to the d, R is 0 by the way, d minus 1, and these were equal to 1, so maybe I don't have the 7. And then you see that's the power of 2 that I was talking about, because so far we don't have a power 2 guaranteed, because at least I have an 11, 13, and so on, or 5, or 13 here, or 17. That's the only position where I can get a power 2, and it will only be if d equals 1. Okay. Then now I'm in position to apply this guy, so that would be L to the n, and m to the d minus 1, and n, and then finally we get the 3 to the n. It just copies this guy, 3 to the n, 5 to the n plus 1, 11, okay. And then whenever I have a 3, a 5, and an 11, I can apply the EF, or 3, 5s, and 11s. I can apply an EF, and the EF basically just removes all the 3s and puts it into the 7s, and then change the 11 to a 13. So this guy will be an EF to the n, and then a k. So that will be just put this in the 7, so it'll be 7, so it'll be 5 to the n minus n plus 1, 5 to the 7, and then the 11 will become a 13, which is exactly what should be in the end here. Okay, so that's already showing this. If R is positive, then what we can do here is apply, do you want to have to apply, because R is positive, is this guy. So it will cancel one of the R's here and remove the 17. So it would be a 2 to the n, 3 to the R minus 1, minus R minus 1, 19. And in this situation, I can apply a DG. How many times? To the number power of 2. So n and then an h. And then what it will do is just it will just remove everything there is in 2, put to 5, and add 7 by 1. So that will be 3r minus 1, 5 to the n, 7 to the d minus r, and it will change the 19 by n 11. Okay, that's it, yeah? And then now I'm in position to apply the EFK, because I have 2, 5, 7s, and 11s. So EF, how many times I have to apply R minus 1, K, And then what it will do is just copy everything to sevens, basically. And so that would be a 5 to the n. Yes, 7 to the... So when you copy everything, then we just have d minus 1, and it will change 11 by 13, which is exactly what it should end. Okay? So this shows the claim. And basically finishes the proof. So this FRACTAN gang is a prime generating function, which is a very nice result, and I hope you enjoy this lecture. See you next time.